Welcome back. In today's short video, we're going to be covering a very important concept when it comes to ABG interpretation that I think causes a lot of confusion if not properly understood. Let's take a look at a standard ABG strip. Now, what confuses most people about ABG interpretation is that they don't realize they're looking at two separate systems on one strip of paper. So let's separate these out and make it a little easier. So on the left side now, we have the parameters that affect the patient's ventilation and acid-base status. And on the right side, we're looking at the values that affect the patient's oxygenation status. Now, let's start on the left side with pH. And pH is the measurement of hydrogen ion in the patient's serum. And that actually equals the negative log of the hydrogen ion concentration. That's what this lowercase p denotes, is the negative log. So it's an inverse logarithmic scale. And if you're not familiar with the pH scale, I highly suggest you go back and watch the video on the pH scale that I've linked here. The next value we're going to look at is PCO2. Now that's a capital P. Anytime you see a capital P, that's a partial pressure of a gas. So this is the partial pressure of dissolved carbon dioxide in the patient's serum. In order to understand partial pressures, you're going to have a really good understanding of Dalton's law of partial pressures. And if you don't remember that concept, I've also linked a video to that here. Next, we have the bicarbonate level. Bicarbonate is a primary buffer in the patient's serum. But you have to be careful because this value of bicarbonate on the ABG strip is not measured by the analyzer. It is estimated based on the Henderson-Hasselbalch equation. If you want to know what the actual measured bicarbonate is, that's going to be found on the renal panel, not on the ABGs. Another thing to keep in mind is that the bicarbonate can vary whether or not a patient's in an acute or a chronic acidosis. And the bicarbonate can also vary based on the CO2 level. So that's where base excess comes in. Base excess is a value that gives you the true state of the metabolic side of this acid-base equation. And we'll discuss these parameters in detail and how they interplay in another video. So now taking a look at the right side, we do have PO2, and remember that's a capital P. So this is also a partial pressure. This is the partial pressure of dissolved gaseous oxygen in the patient's serum. Next we have the SaO2. Now a lot of you are already familiar with SpO2, and that is the saturation of hemoglobin in the patient's bloodstream as measured by pulse oximetry, and that's where the P comes in. But this is SaO2, so this is the saturation of hemoglobin as measured chemically by the analyzer. So instead of using a light shining through the finger, like in the SpO2, this is a chemical analysis. And FiO2 is the concentration of oxygen that you're delivering to your patient. This abbreviation stands for the fraction of inspired O2, and that's going to be in decimal format. So room air is 21% oxygen. The FiO2 on room air would be 0.21. If you have a patient on 100%, that's going to be 1.0. In upcoming videos, we'll be dealing with each one of these systems individually and go into these values more in detail. So stay tuned for those.